Okay, it's 10:05. Let's begin. Hi, everyone. Welcome to the third lecture of our diffusion clustering IAP. And today we are going to talk about conditioning and guidance of diffusion models. So here is the outline for today's lecture. First, we will talk about conditional diffusion. And then we will talk about some empirical hacks to achieve conditioning a diffusion model. For example, nowadays, modern diffusion models are always language conditioned or some other thing conditioned. And we are going to talk about two empirical hacks called classifier guidance and classifier-free guidance. They are actually very critical to modern diffusion models. And all modern diffusion models you see nowadays use these two techniques. Finally, we are going to cover some modern architectures for conditional diffusion. So in previous lectures, we are talking about how do we train a generated model that we can sample from PX. That is the distribution of your data. If you are generating images, PX is a distribution of all images. And today we are going to talk about sample from a conditional distribution, PX conditional Y. For example, if your conditioning variable Y is a class, for example, cat or dog, right? Previously, you just want to generate images of arbitrary things. And today, given some conditioning label Y, for example, specifically ask your diffusion model to generate dogs, then your model should generate dogs. There is an obvious way to do this. So just like in conditional prediction, neural networks are able to take in extra input Y. So one intuitive attempt is that instead of letting your diffusion neural network take in only XT, that is a noisy version of X, you can let it take in both noisy X in your label Y. So this is the intuitive way. Theoretically, if you train this, it's likely that your neural network can just learn something reasonable, but it's not good enough. In fact, large diffusion models don't even work with, there's one interesting fact. In fact, large diffusion models don't even work without conditioning. So you may think that, okay, we've looked at the sort of math about like how to sample from PX with diffusion models, but in reality, everybody is doing PX conditional Y, that is conditional diffusion. If you don't input a language, this model don't really work very well. Why is this? This is because the unconditional distribution of all images is just too big for the neural network to learn. Like only when users like input some language conditioning does these models figure out the distribution reasonably well. So in fact, it doesn't work without conditioning, and we humans also want to have some control over the model, so it's ideal. So let's use the easy way to generate some photo of animals. I ask you to generate a cute dog, and this is the result. You can see that the result is really weird. You can hardly identify any dogs in some of these pictures. So the easy way doesn't really work very well. And here is a takeaway. You can just add your conditioning variable during your training by concatenating that to your neural network input. And you can treat it as a kind of treat it as like a regression problem, conditional regression, like predicting your score, conditional on some label Y. It works in some cases, especially in low-dimensional cases. For example, like in later lectures, we may see the things like diffusion policy or those low-dimensional cases. But it doesn't work in practice when you actually scale this up. Like all the modern architectures don't just concatenate your conditioning variable. And finally, there is, however, one nice thing about conditional diffusion. So just like regression, if you just concatenate your Y into your neural network, you're actually predicting an unbiased distribution that is PX conditional Y, because by definition, like this is exactly doing that. Okay, is everybody with me about the high-level objective? Any questions? Okay, so then we are about to dive into the second section, which is a slightly more math-intensive. First of all, how many people here like know Bayes rule? Okay. How many? Okay, great. I think most of the people know this to some extent. Then we are going to dive into probability for the second section. Okay, so we are going to talk about classifier guidance. And basically today we have 4 sections, and 2 sections are specifically about guidance. What is guidance? Guidance is a technique that lets your model to condition on something stronger than the easy way. And it is a technique that is critical in all modern diffusion architectures. Previously, we proposed an easy way that we led, previously we already talked about unconditioned diffusion models where your diffusion neural network only takes in your noisy X and try to output a clean version of X. And in earlier slides, we talked about easy way of just concatenating Y into your diffusion model. So now let's consider a slightly different objective. Let's say that at training time, you are allowed to train a diffusion neural network that can denoise your noisy X. So just like before, just like all the lecture before. So that is a given setting. However, this time, at sampling, we want to sample from Px conditional Y without retraining your model. So you're actually given an unconditional model, but I want you to sample conditionally. How can we do that? So here is a trick. Everybody knows the Bayes rules, and let's take a look at the distribution we want to sample from. So as I said earlier, our distribution is Px conditional Y. And this term can be rewritten into Py conditional X times by Px over Py. Does everybody get this? Okay, great. And then you just take log on both sides of the equation. On the left-hand side, you have log Px conditional Y. On the right-hand side, you also expand this term out. And then you take gradient with respect to X on both sides. What will happen is that you can see that this is a term we try to approximate with our neural network. This is a desired sampling distribution that is a conditional one, right? And on the other hand, we have this nice term here. That is a diffusion score that we previously calculate using our unconditioned diffusion model. And now our desired term and our given term are both appear in the same equation. Then what happens is that it suffices for us to figure out this term in order to approximate the desired term from the given term. And we can take a look at what is this. What is this? Y is a label. X is your like image. What does this look like to you? It's a classifier, right? However, this is also not as simple as a classifier because in diffusion models, what is your X here? What is your X here? Your X is actually not your clean image X, right? Your X is the score, the score term for diffusion here actually takes in your noisy X. That is your XT. Your gradient is also respect to XT, right? So in reality, this is somewhat like a classifier, but on the other hand, it is also a classifier on noisy input XT instead of a clean X. So that is a thing to keep in mind. Okay, now we've noticed that, and let's just assume that we have such a classifier for your noisy X. What will happen? Now let's do it for noisy X in diffusion. So I want everyone to consider this term. This is a joint distribution of XT and Y. So that is, you are trying to synthesize, you are trying to sampling from the joint distribution of XT and Y. And previously, we talked about we can do this decomposition, right? And here, you can rewrite the joint distribution into the unconditional diffusion score plus your guidance score. Sorry, your classifier score, noisy classifier score. And then you can just take gradient, and this term is what we learned earlier. This epsilon is what your diffusion neural network outputs. And of course, like there are some other terms, constant terms here. And here you just take a gradient with respect to your noisy classifier. And finally, you put them together, and you can modify the score of your diffusion model into this modifier term by incorporating a classifier. As a result, this is what it looks like. So just one thing to note here. We can do something like this in order to achieve this conditioning, right? However, this has some direct empirical interpretations. However, what people do is that there is an empirical hack saying that, okay, this is a term we previously want, right? And this is a conditional bias. Like by adding this, I'm biasing this distribution towards a conditional distribution, right? If you put a constant 1 here, right, this is directly translate to a very meaningful conditional distribution. But there is one empirical hack that people always do. That is, they put a constant here, usually called S or gamma here, that upweights this even further. Like instead of having it 1, basically people say, what if I just put like 1.2 here, 2 here, such that it is biasing my distribution like even stronger towards a conditional one. So that is one empirical hack people do. And what in reality, like by putting it there, what people are actually doing is that like there will be sampling from px conditional y like to some like to the square and divided by px or something. But basically, the intuition is that by putting a constant here, you will be able to condition it stronger with a classifier. And we call that constant like sometimes we call that guidance scale or like guidance strength. Okay. So in reality, what people do, so previously, let's say you can predict some distribution for xt minus 1 using like your diffusion parameterization. That is, you predict the mu for the less noisy x, and you also have a variance matrix. But with a classifier, what you do is that you just take gradient through the classifier, you multiply it by the guidance strength, and you add it to the mean. So it's making some modification to x such that at test time, you will bias the sampling towards a conditional distribution. And this is quite useful because you can actually, as soon as you can write your objective into a classifier, you can do a lot of fancy things. So in the case I talked about, you condition it on like cats and dogs, right? But in general, like you can generalize this to many other classifiers. For example, in later lectures, maybe in special topics, we may talk about diffusion planning, and you will see that like you can write like a reinforcement learning like a value function or like success rate into a classifier. And if I have a classifier on success or failure, then I can use classifier guidance to guide the model to plan a successful trajectory for us. So this is a generalization of it. And here is also a visualization of what it's actually doing. So here is a original distribution, px, that we are trying to sample from. And you can see that it is a mixture of 3 Gaussians. And here I start to add guidance, specific classifier guidance. And what will happen is that if I add guidance, sample from each cluster and like overlay the 3 clusters together, what will happen is that you will witness a picture like this. That is, we modify the original unconditional distribution by pushing each cluster of the distribution towards their own center. And then you bias the distribution like this, leaving more space in the middle. And as you add more guidance, you will realize it will just go further and further. Okay, here is a takeaway for classifier guidance. You can train a classifier on noisy input X. And this is usually undesirable because why do you want to train a separate classifier and also it is on noisy X, not like really X, right? It is actually really confusing for the model. If you as a human look at a quite noisy image, you cannot determine what class it is. It is very hard. You cannot determine whether it is a cat or dog. So there will be a lot of variance in the training. It's undesirable. And also, at sampling time, once you get this classifier and your unconditional model, you can compose the score of this unconditional model and this gradient of the classifier using the previous formula. And then after you compose them, you can sample it with a composed score. What does this allow you to do? Is that you can now do conditional sampling without training a conditional model. I give you an unconditional model. You only need to train a noisy classifier, and then you get a conditional model. However, as you see earlier in this picture, adding classifier guidance can bias a model towards some distributions that looks like this. This differs from the ground truth distribution we actually want to approximate, right? Why do people still want to do this? Of course, I want to do conditional sampling, but there are many other reasons. Sometimes you will find that generating images using a picture like this is actually more favorable, because many people don't care about matching the original distribution of all images. They only care about generating high quality samples. And there are two very different objectives. If I only care about generating high quality samples, then I don't want to generate less likely images, just like the original distribution, right? I want to sample differently. So if you apply guidance, you're adding some bias into the model such that it is not sampling from the original distribution here. That is what I mean by biased distribution if you use a higher guidance strength. Finally, you can see that classifier is really limited. So far we talked about, it's a classifier. And classifier is usually, you need to formulate your problem into discrete classes or binary classes. And you can see this is quite limited because modern neural networks, modern diffusion models you play with, like either it's OpenAI DALI, Sora, like all those diffusion models. What they do is you don't input a label like dog or cat. Instead, you put a free-form language. And furthermore, what people actually do is you can even input a existing image and then ask your diffusion neural network to modify it. And all this conditioning inputs, like images or language, they are not really discrete classes, which means that we need something better beyond classifier guidance. Then there comes classifier-free guidance. Classifier-free guidance asks a slightly different question. So in previous lectures, we talked about unconditional generation of X. And now we want to generate X better without retraining a classifier on noisy X. That is, we stick to the very original objective of diffusion, generating X better. This is not even conditional yet. And I also want to generalize beyond class conditioning, and we want to do that like language. Sorry, maybe I should spend a bit more time on this. You will see later that classifier-free guidance is not only extremely useful to do conditional sampling, but also you will find that classifier-free guidance is important to improve the sampling quality overall. Just like in this example, you may view classifier guidance as a way to generate from this one cluster very well, but when you overlay the cluster for all three classes, you will end up with a distribution like this, right? And for classifier-free guidance, it's usually it's not only that I just want to generate from one cluster. I actually want all three clusters together by putting all the classes together, and I claim this distribution is better than that one, as you will see later in the slides. Is everybody with me? About the high-level objective differences here? Okay.
Sorry, a couple questions. So, is using classifier guidance better than individual models for each class?
That is a good question. I think it really depends. Usually when you're, so I first talk about the easy way, right? And usually you can, for this three-class model, you can just train 3 easy way models. And if the dimension is low, if each individual cluster is a distribution that the easy model is already good at, then you are good. which usually means that whenever your X is low dimensional, the easy way usually just works. However, this is first wasteful because you may have a lot of classes, right? Secondly, if your each individual cluster corresponds to still a high dimensional manifold of data, for example, cat and dogs, it's still challenging for the easy. It could still be challenging for the easy way. I will have a visualization as probably after classifier-free guidance that shows you like the effect of guidance and like what if you have no guidance and just train individual models. But I think usually like there are two reasons. First, you have efficiency reasons. If you have 100 classes, you don't want to train 100 different models. Second, even if you break it down, it could still be challenging.
Yeah. So let's say you want to get a condition so that you've got an image that has a dog and a cat in it. I imagine that like if you use classifier guidance, that might fall sort of in the middle, I guess, of your image there on the left. But does that mean that if you use classifier guidance, it's going to get worse? Yeah. Like modeling something that's a joint between two different classes.
So I think, so first of all, an image with cat and dogs will be also like out of distribution for the classifier, right? Like if you are a human annotator, you cannot really annotate this very well. So I think first it's strictly out of distribution data. And I think what will happen is that your neural network may make a guess and steer the sampling like towards one of these clusters, then eventually give you an image of just one dog or one cat, by ensuring that it is high quality. Like if your model like pursue something in the middle, if you don't add guidance, you'll actually probably not see something that contains a cat and dog. You'll probably see something that is like a weird animal, like that you cannot identify. And obviously, when we humans see something like that, we see, this is a weird animal. It is a bad image. It's obviously AI generated. And that's actually one reason why people want classifier guidance, right? Like, because it steers you away from something ambiguous and towards something people say, okay, I cannot identify this as an AI generated image.
Thanks.
Okay, any other questions? We have plenty of time today.
I keep hearing you say, you use the term high quality. Does that mean that it's high resolution, or does it mean it is the low FID score?
It's like a low FID score. Yeah. We are talking about fixed problem. Like when I say generating PF from PX, we are saying generating from the distribution of our original data, and by that we mean that the problem is already fixed. If your original data is 1,000 by 1,000, then you want to sample from 1,000 by 1,000 images. So we are not really comparing against like different resolutions. And we will talk about low temperature sampling later, which explains what is high quality. Okay, any other questions? If no, we are going to dive into classifier-free guidance. Okay, it's a slightly different objective. Now we want to use guidance to even improve unconditional sampling, like not just conditional sampling. Okay, previously in classifier-free guidance, we used this formula. That is, your gradient of your log probability of conditional distribution can be decomposed into this term plus that term. So this is a familiar like unconditional distribution score. This is your classifier gradient. This is a reason why we need a classifier. And as I said earlier, such a classifier is highly undesirable, and we want to get rid of it for many reasons. For example, it can only handle discrete classes. You have to train it on noisy images, which is really weird. And third, like people just don't like to train a separate neural network. And to avoid doing that, let's tackle this difficult term. So this is a classifier term here, and still, we use Bayes' rule again and see what we'll get. We rewrite it into Px conditional y, that is a conditional distribution, and with the two Px and Py. And we like before, we take log and we take gradient. So after you take log, you will notice that here's a term that doesn't involve x at all, right? You can just cross it out because there's no gradient with respect to x. So what we end up with here is that our original term we want from the noisy classifier is this. And you can decompose it into gradient of x log px conditional y. That is a conditional distribution, and minus like your unconditional distribution. So I want everyone to remember that this is an alias for the term that's circled in red, okay? Because this term is about to appear again in the next slide. Okay. Last slide, we have this. And we can plug it back into the gradient for classifier guidance as shown below. This is a formula for classifier guidance. Make sure you recognize that. And now, this is a term that appears here. So we replace this difficult term by plugging in this formula here. And what do we end up with? You'll see that if we combine these two things, you'll end up with a term that looks like this. So in your previous slide, you will actually not previous slide, I already copied it here. Okay, this is yeah. So this is classifier. This is classifier guidance. So classifier guidance says that you can add a score of unconditional distribution plus classifier gradient, right? And now classifier-free guidance, classifier gradient is rewritten here. Oh, sorry, oh yes, it's rewritten here. I made a mistake. You can replace that like, you use this formula and plug it into the second one. And what you end up with is that you modify the classifier guidance term, px conditional y. It was originally unconditional distribution. It used to be here, this term here used to be the classifier gradient. Remind yourself, this used to be the classifier guidance. The classifier gradient, right? And now we say we want to get rid of it using a previous formula from Bayes' rule. And now we just replace it with px conditional y and px. Is everybody with me? I saw some confusing faces. But this is really just combining the formula and rewriting things together. So what does this say? We start with the motivation of classifier guidance. There is one difficult term in it, namely the gradient of the classifier. And using Bayes' rule, we rewrite that difficult term into the terms we already have. One of them being still the original unconditional diffusion. The other is a score from the easy way, right? At the very beginning we saw this. It's just concatenating your y into your neural network. And use that unbiased distribution. Like, are people with me? I just want to make sure everybody actually get this math correct. Okay, and just like before, this term replaces the gradient for the classifier, right? And this is a term that's used to bias the unconditional distribution into the conditional one. So if we want to add a strength here, guidance strength here, we add it to this classifier term. And of course now it's decomposed, but we still add it here. Okay? So if you want your guidance to be stronger, you turn this gamma to be much stronger. If you don't want to steer it towards a like certain conditional distribution, you don't add this gamma.
What is the typical range of gamma?
It can be quite wild. If you just want to do unbiased sampling, you set it to 1. And what you will end up here is the easy way formula. However, people typically find that like you can use like 3 or 6. I think people use 6 quite often. Actually, 6 is a crazy value, isn't it? Like it basically says like your you're really guiding it really, really strongly. Yeah, because you can see that unbiased distribution is just 1, and like if you use 2, I was already say like it's a weird distribution. Now if you use 6, it's really, really weird.
So, but you're saying then you would train one unconditioned model, and then that's the one, the gamma gradient of log dx of y is the easy way to train conditioned but just with concatenated y.
Good question. Okay, what's your name? Yorgos. You make a really good point. So if you look at this formula, you need to train 2 neural networks. One is already the unconditional one, right? The other one is a conditional one that's trained using the easy way. And you compose a score of both models. And you will see in the next section, like how do we actually do this? But here we are actually training 2 neural networks to approximate the distribution we want to do in classifier-free guidance. Okay, any other questions? Great. So here is the final form of classifier-free guidance. Now, instead of doing X, we are saying more rigorously. We are using XT, that is a noisy version of X. And you can see that if our neural network predicts the epsilon prediction, that is predicting the noise, what we'll end up with is that with all the math before, we are going to modify this epsilon term. So let's say our neural network is trained with conditional label y, and this is the epsilon. This is a conditional neural network that's done the easy way, and we take its output times some constant, and we take the output of your unconditional model times some constant, and we add them together to form the final output of your neural network. It's like you combine the output of 2 diffusion neural networks together to get your final one, and sample with the final one to achieve your sampling for classifier-free guidance. And here is a typical term people use specifically for classifier-free guidance, that is omega. And it's like you put omega plus 1 weight on the conditional model and minus your omega times unconditional model. And intuitively, after you write this out, you will find that what classifier-free guidance is doing is that it is upweighting the score for the conditional model and while pushing it away from the unconditional model. And this is actually exactly like the picture we just saw earlier. That is this one. So we are pushing the entire distribution more towards the conditional model and away from the unconditional model, that is the center. And in images, people use omega value of 6 a lot. Yeah. And what is the effect of this? If you just sample from the easy way model, what you will end up with is low quality pictures like this. Here we are asking the model to generate a panda on like a colorful glass panel. And what you will see is that these pandas on the left-hand side just look really weird to us. And as a human, I would definitely prefer like this more saturated images, but with a nice looking panda face. So this is the effect of that, and we'll get a deeper understanding of that very soon. Another example, I'm trying to generate a sitting room with a picture of the corgi on the wall. And on the left-hand side, you will end up with many pictures that looks like this. And you will see they are slightly, that's very weird. Like if you look at this image, you cannot find the corgi photo. And here you just generate a corgi instead of a photo of a corgi. And also the pictures doesn't look as appealing as those on the right. And on the right, it is with classifier-free guidance, in fact with a much stronger scale, and you will end up with is this nice looking pictures as you want. So all modern diffusion models actually use classifier-free guidance, and it's actually quite important as a trick for you to sample good images. Now let's try to understand why is it good. So previously I've talked about biased distribution, like quality and like all these abstract terms, right? And let's understand why does this empirical hack improve the sample quality. Usually our distribution Px is a directly desirable outcome. You want to sample from all the images you use to train your model. For example, let's say I just train models like on all the internet images. But then you will immediately realize that the entire like online image contains a lot of low quality samples. And we humans naturally prefer like more professional photography. We want to generate something fancy, right? So actually, if you stick to the original internet image distribution, you'll realize that this is actually a not quite preferable distribution you want to sample from. If you sample from it directly, you can sample like some random pictures. The data set is bad. And however, we also know that among this distribution, there of course most of the data is good. And most of the good data like have some certain traits. And what we are essentially doing is that when you sample from the distribution, you want to be more conservative about it and do low temperature sampling. And low temperature sampling can be understood better in language model. How many of you know approximately like what is language model? How does language model work? Okay, so imagine that you are language model and are trying to predict the next word. For example, let's say I give you something called I picked up blank from the table. And if I want to predict a blank, I can write out a distribution over the entire dictionary. For example, I picked up the apple from the table. I picked up the phone on the table, something like that. And obviously, you can assign a number to each of this word. For example, you can assign like 0.6 probability to phone. You can assign 0.1 probability to Apple, 0.1 probability to remote controller, something like that. This is a ground truth distribution you want to sample from. However, what people actually do is like, because phone is with 0.6 probability and is the one with largest probability, I always output phone all the time. That's sometimes what people do, like when they want to generate really high quality samples. Is everybody with me? It's like there are regions with higher probabilities, and instead of sampling them with just like that specific ground truth probability, like I upweight the probability there and downplay the probability on like less likely terms. And then I end up with terms that are actually like very, very likely. And it is also the case like in internet images. Let's say most of the images are good. Like there are some long tail cases that are bad. So what I do is like, if I can model the original distribution really well, I just reweight the original distribution such that the high probability cluster have even higher probability, or like I just sample from them all the time. And obviously this is very easy in language space because you have a probability distribution that looks like these pictures. Let's say like this, it's like this. You can just scale it to something that looks like this, such that the most likely term is sampled almost all the time. It is easy in discrete because you can just, for each entry, you just scale the largest and take exponent, like something like that. However, for diffusion, it's quite unclear, isn't it? It's continuous data, and you are sampling in weird ways, not just like, it's not something you can just scale. And in fact, what you are doing with all the guidance here is exactly low temperature sampling. By saying that, I want to upweigh the more likely ones and push down the weight for less likely ones. And as a result, by doing this, you are no longer sampling from the ground truth distribution, but you are sampling from the more likely distribution that contains like images that you would like to deem as good images, more likely. Is that clear to everybody? Low temperature sampling. Okay, great. Let's take a deeper look inside guidance. Of course, everything comes at a cost. As I said, you have low temperature sampling that generate more visually appealing images. However, this also comes at a cost. As I said, this is actually a biased distribution that doesn't represent the true distribution. So if you have a ground truth distribution that looks like this, like with all the tree branches, you can see the tree branches data set is, like each data point is one like dot on this tree branch. It's like a 2D coordinate or something, okay? And this tree is highly multimodal. It's like a very difficult distribution, like for a small neural network. So if you just like naively train your easy way model, what you end up with is something that looks like this. You will have a lot of outliers here due to like the limit power of neural networks. And just like I said, like in the low temperature sampling example, these are the samples that you want to discard. And of course, they happen at low probability, but you still want to completely avoid them, right? So what you end up with is that you apply your guidance to it. And you can see that if you sample from the guided thing, all your points lies in the tree branch as expected. However, you can also see that avoid sampling from some tree branches completely. So this is what I mean by biased distribution. You are actually sampling from a biased distribution that doesn't represent the original distribution. However, because everything lies in the tree branch, as a human, as your user, they might prefer this way over this way. So is everybody with me? Okay. Here is a summary of classifier-free guidance. You want to train an unconditional model and a conditional model together. And you sample by subtracting the unconditioned gradient from the conditioned gradient. You assemble the score from both models to get your final score and sample with that combined score. It is still biased because it doesn't sample from the true distribution. But first, it doesn't need a classifier anymore. Second, essentially doing low temperature sampling, but for diffusion, which can improve your sampling quality despite the bias. And finally, it could trade off between fidelity and diversity. You can see that like here, I'm actually reducing the diversity of my sample because I'm less likely to sample from like local likelihood regions. But the fidelity, the score, the quality is much better. Finally, I want to say that if you take a look at our formula here, you are combining the easy way model with unconditional model. And here, does y need to be a class? It doesn't. Because your easy way model only says that I want to take in y, concatenate the information of y into my neural network. But here, y can be something general because we are not really taking gradient through the classifier. We're just taking it from the neural network. So if you have a language instruction, what you do is that you embed your language instruction into a language model, and your language model output a vector that is probably like 4096 dimensional, and you just concatenate it to the neural network, feed it to the conditional neural network all the time. And you can do classifier-free guidance on top of that. You achieve conditional language very well. So in classifier-free guidance, we generalize beyond it, beyond classes, and we can now like do anything conditioning. Okay, is that clear? Okay, let's talk about how we do this empirically. As I said earlier, your diffusion models in classifier-free guidance has to be two separate models, one conditional and one unconditional. But in reality, training two neural networks is just like very wasteful. In fact, there should be a lot of parameter sharing between them because the generation power, like between these two, they are like kind of shared. And what people do in reality is I just combine these two models into a single one. And here is what people do in stable diffusion. If you take a look at this, this is a reverse diffusion process. What you do is that you start from some Gaussian noise here in latent space, of course. And here you have some conditioning variable. So all these conditional variables are embedded by some small neural network into a conditioning vector. And then this conditioning vector is sometimes concatenated to this Gaussian noise to begin your diffusion. But sometimes you flip the switch to this way. Oh, sorry. Oh, sorry. I think I talked about the wrong picture. But basically, sometimes you drop out your conditioning variable. Sometimes you don't, and then feed whatever input you have like to your neural network. So it's like your neural network is trained to handle unconditional input and conditional input at the same time. So typically, usually you have a weight like 0.1. But with 0.1 probability, you just completely drop out your conditioning. With 0.9 probability, like you feed it with conditioning. And then your same neural network is trained for both objectives. And at test time, of course, you can turn the switch. And now you can sample with unconditional score or conditional score, and you combine them together. Sorry, I think the picture is for the section 4, actually not for the empirical like switch. It's actually slightly different. But basically like that, you use the same neural network to represent both objectives. Okay, is everybody with me? Okay, and here is a picture of how people do conditioning in practice. This is called UNet. This is quite widely used, and in diffusion, this is a specific design for diffusion UNet. You feed your conditioning like into the denoising UNet at different levels. What this architecture does is that it's specifically designed for images. And at the beginning, like you have your noisy image, and then you feed it into some conv layers that is conv layers that sample it down, and then you do some like spatial attention over all of them, and then you conv it down like something like that, and you compare the earlier features to the later features, just like traditional UNet in deep learning. There are other ways to feed in conditioning. So this is diffusion transformer. So I think everybody have heard of transformers. And we know that transformer has been applied on images in terms of VIT. What that does is basically dividing your image into different image chunks, like small patches. If you have a large image, I just crop into this chunk, this chunk, this chunk, this chunk, like each patch. And I feed the patches to a transformer and let the transformer like train, be my backbone. And in diffusion transformer, what's special is that if you want to condition on something, instead of concatenating your condition into input tokens, what people actually do is that you feed your condition into some multi-layer perceptron, and the multi-layer perceptron outputs some parameters that you use to scale and shift the intermediate layers, like in the token branch. Okay, this is the architecture. And of course, people can do cross attention too, but like this is what people actually do. And there are also alternative, like easy architectures that are investigating this specific paper. You can also just concatenating conditioning into a sequence dimension, like I said, in the easy way, just concatenate, right? But like what people do in reality is that I always apply some MLP on the conditioning, and this MLP outputs some like scaling vector and shift vector that I add to this. So it's like if the output of layer norm is called Z, and then like what I do is like gamma is conditional conditioning, beta is conditional conditioning. Then what we end up with here is gamma times Z plus beta, where gamma and beta are functions of conditioning. That's how conditioning is applied, like in this architecture. Of course, there are also trade-offs. For example, people say that this trick here, like called adaptive layer normalization, like they have problems for fine-tuning. If you have some conditioning at training time, and at test time you want to fine-tune it for some different conditioning distribution, this is actually more numerical unstable than like this approach. And finally, there are also interesting techniques called control net, and that is saying that let's say I have a pre-trained diffusion model, for example, stable diffusion. And now at test time, I want to add some control. For example, stable diffusion, like is a model tailored for text to image generation. And now at sampling time, I want to make a model that condition on other things. For example, I can draw a human skeleton on a blackboard, like with just like draw a stick man, right? And I want to generate a human that align with a specific human pose. And my original pre-trained model isn't tailored for the application, but I want to get a model for the application. What people do is that they can use control net. Basically, let's say you have a pre-trained neural network that is stable diffusion, and each of the neural network block basically look at this. You have X to Y mapping, and now in control net, for every block that looks like this, I make a copy of it here, and then I freeze the original parameters here, and I keep a trainable copy here, and I only fine-tune this branch on some small data sets that contains like human skeleton and clean image pairs. Okay, I fine-tune this copy here, and like with the objective that the output of this small control net copy plus the original output will fulfill my objective. So basically, it's like just like LoRa fine-tuning. You're inserting some like new parameters to your original pre-trained neural network, and you only train the added parameters for your downstream objective. Okay, and it has some special tricks called zero convolution that's initialized with zero weights. But all these tricks are done to maintain, to ensure that at test time, when you are sampling, when you are like fine-tuning your model, you don't catastrophically forget what you already learned in the pre-trained model. It's like you are only adding some small novel skills to your original model instead of asking it to forget everything before and just learn this. So this is how it's achieved. And I would highly recommend people to read control net because it's quite useful in image diffusion models. There are some extended readings. So I highly recommend this blog, Guidance, a cheat code for diffusion models. If you visit our website and access the slides, you will be able to click into this. You can read the original classifier-free guidance paper. I will also add some other papers, like for people who are interested in too. And that's the end of this lecture. Questions will be appreciated, and we'll also send out the survey link very soon.
For your guidance string, say I introduce my guidance string to some arbitrarily large number. Like what happens, like what's the behavior of my diffusion model then? Is it right to say that as my guidance string becomes arbitrarily large, I'll be only generating the same image over and over again?
Actually, not really. First, you will realize it generates very bad images. So because as you see here, like if you look at the picture here, you're pushing it away from the center, from the unbiased distribution. And as you can see, if you add it so much that it's got pushed so far away, it will be bad. It will have no overlap with the unbiased distribution. And in fact, like whether you generate the same image actually doesn't really make sense because your manifold is extremely high dimensional. And what classifier-free guidance says is that I push it towards a certain class. It can only guarantee that you condition on the class stronger. But each cluster is still like so many points here, right? So there is no guarantee that you will end up with the same image. Which can only guarantee that you end up like with a class like more and more likely in the extreme way.